This particular unit goes through and they talk a lot about what are known as acid derivatives. So if we're looking, we've got a carboxylic acid. So if we're going to start our focus at looking at acid derivatives, one of the first things we'll look at is, well, what are acids? So we get a lecture which should be mostly review looking at carboxylic acids and that chemistry. We'll double back to that in a second. And then kind of the second majority part of this is talking about acid derivatives. So derivatives is just a way to say that you're starting with an acid, or you're starting with something and you're changing it, you're mutating it into something else. So if we were going to talk about acid derivatives, we could theoretically say from that starting structure that this compound would be an acid derivative. So the only thing that I did was I changed the CH3. I derived something from that original structure. That's way too broad of the explanation behind this. Right? And you might be able to tap into why that's way too broad. If we're going to look at the carboxylic acid, where's our primary chemistry going to be centered at? I would argue we're at two sites.
The oxygen on the OH, and then carbon, positive carbon.
All right, I'll give you the positive carbon. So the positive carbon of our carbonyl is actually is absolutely going to be an important site, looking at a partial positive. And then it's not the oxygen that we really care about, it's the hydrogen. Why? Because it's an acid. Okay, so those are our two kind of primary chemistries. And if we go through to look at the quote-unquote acid derivative that I went through and did I leverage either of those two chemistries? No. Okay, so I was way off base on that. So when we're thinking of these acid derivatives, we're really trying to reference kind of where that core functionality, that core chemistry is coming into play. And so really what they're keying in on when we talk about acid derivatives is the reactivity of that carbonyl carbon. That carbonyl carbon, if we kind of cheated and looked at resonance, we've got an electrophilic site there. Whoa, and I added an extra carbon. An electrophilic site. And if I had a nucleophile, I could potentially have a nucleophile come in and attack. We'd break the pi bond, and then we could remake the pi bond and kick out our OH. So for those people in lab on Tuesday, we talked through that kind of detail, that mechanism. For those people in lab on Thursday, we'll talk through it again there. For those people not in lab, that's why we have the lecture videos that go through and talk all through this. Okay, so when we're talking about our acid derivatives, the primary thing that we're considering is how we modify really the tail end, this section, okay? What goes in the box? That's going to be our acid derivatives. Right? And the things that go in that box are going to have an acute or a high level effect back towards our carbonyl carbon. So when I say high level effect, what we're saying is that whatever goes in that box is not carbon or hydrogen, because carbon and hydrogen aren't having a huge effect on that carbonyl carbon. Okay, so that's kind of what we talked through on Tuesday, where you guys went through and said, well, we could have the OH in there. That was your carboxylic acid. Several people threw in OCH3s. We now had esters. Okay, you could throw in a nitrogen. We now have amides. So what we're talking about within the acid derivatives are all those possibilities. And then what we end up exploring is, to a couple things, how is that affecting the carbonyl carbon? And then what are all the reactions that we can run? And so for each of those new derivatives or functional groups, because they're technically functional groups, what we end up doing is repeating unit 2. So you'll look at unit 2 for amides. You'll look at unit 2 for esters. You'll look at unit 2 for carboxylic acids. So all of those exact same chemistries come up again and again and again and again. So it should feel very, very, very repetitive. It's now just trying to figure out where their subtle differences. Those subtle differences ultimately tie back to how they're affecting our blue carbon. Kind of, sort of? Before we get into the acid derivatives, we do have a conversation about acids, because that's where this kind of started. Acid derivatives, our first word is acids. So what's going on within that? Several people went through and did the quiz already, or the play pause it lecture on it, and one of the questions that pops up very quickly is that when I talk about acids, what are we talking about? Right? And we want to make sure that we're centered on that same concept, because we don't want to get confused or lost in our language. Right? When we're talking about an acid, it is very specifically, or at least when I'm talking about an acid, very specifically referring to the Bronsted-Lowry definition. Okay. Why not use the Lewis definition of an electron acceptor? Because that is also an acid. Why can't I use that definition?
Not specific.
What is the carbonyl carbon acting as? A Lewis acid. So if we use the term acid as Lewis acid, we have no specificity over what site we're talking about reacting. So it's why I don't like the Lewis definition. This is why back in OChem 1, I tried to get you to not look at the Lewis definition and instead talk about acids and bases as Bronsted-Lowry acids and bases, and then nucleophiles and electrophiles, because that allows us to differentiate that chemistry so that when we talk through the chemistry of the acid functional group, we have the acid referring very specifically to the hydrogen, and then we also have the electrophilic site, or the electrophile, which is going to be referring to that carbonyl carbon. The hope is to clarify our language when we talk through it so that we can be on the same page without having to go through a whole bunch of extra words to explain the specifics of what's happening. Kind of make sense? Okay. Since we're talking about the acid species here, what might be the next natural thing that we might ask you to go through and do? Could ask you about the conjugate base, but why would I ask you about the conjugate base?
It's more important to know if it's acidic.
To know if it's acidic is one option, okay. I keep doing that. Damn it. We'll keep this one a little more simple.
Acids.
What's that?
When you're comparing two acids.
When we're making a comparison between two different acids, we can now evaluate their relative strengths to each other. Okay? So if we're going to talk about acid strength, okay, we now want to deal with how we're going to compare those two structures. Those can be compared from their raw inherent structure. The issue I have with that is that you're now kind of pretending to do things mostly in your head. There isn't a whole lot you can draw out. Okay, that drawing out process, I think, is critical to helping you understand, which is why, and I'm going to regret this. Oh, not too badly. That's not bad. Which is why one of the first things I would tell you to do when looking at predicting acid-base strength is that we should go through and draw out the conjugate base. Because when we draw out the conjugate base, what do we see? Stable what is? Because I can talk about stability at the starting structure.
The conjugate base.
I can still evaluate the stability of the starting acid. What shows up in the conjugate base that I can now potentially manipulate and consider?
Resonance.
Resonance of what? The electrons. It's those lone pair electrons. That's the differential. When I remove that hydrogen, I now have that lone pair. And because we've spent now, where are we at? 30 weeks talking about how electrons move within chemistry or within organic chemistry, we now have a structure that we can say, how can those electrons move? So we could evaluate how the electrons move. We could look at resonance for those options. Okay? we now have something that we can consider and think about moving around. And we could actually draw structures to represent that motion. If we look back to our starting acid structures, we don't have that flexibility. Okay, so it's very hard for us to manipulate because what we're talking about is electrons that are tied up in the bond between the oxygen and the hydrogen. So that changes the dynamic of the question, and it makes it a little bit harder to manipulate. It makes it a little bit harder to apply our rules of stability. Charge, size, electronegativity, resonance, and induction. Okay, so if I'm going to go through and rank acid strength, one of the first things we'll do is go through and look at the stability of the conjugate base. So if I wanted to evaluate the acidity of H3O plus versus the acidity of water, what happens? Well, I'm going to pull off H plus in both cases, and I'm going to look at H2O and OH minus. Which conjugate base is more stable? Water is more stable. And if water is more stable, what does that mean about the acidity, back to my starting question?
Stronger.
The H3O plus is a stronger acid. That reaction is more likely to progress forwards than the other one. We could change our arrow size to explain that. And that would say we get a larger concentration of the H plus. That means it's more acidic. So we're using charge, size, electronegativity, resonance, and all of that to apply these definitions. Okay? Theoretically, you did that in 152. Okay? Whether or not you remember that or believe it is an entirely separate question. Okay? But you evaluated acid strengths. Typically, when you did it, though, you evaluated it based off of pKa, okay, or Kas. You evaluate it based off of the numerical references behind it, not a broader structural interpretation. Okay? So you evaluate it from what I would argue is more factual, but the problem with that factual system is you would have to generate those numbers. Okay? You would actually have to experimentally test all those things. And so what we would like to do is to be able to apply that understanding to a new situation so that we don't have to run an experimental test each and every single time. That's where we doubled back and looked at the structures and said, how could we group these structures? Those groupings are charge, size, electronegativity, resonance, and induction. So it becomes very important to evaluate those. Kind of make sense? Right? So H3O plus and H2O. Is that a hard one for you to figure out, or is that straightforward and easy? Easy? Okay. Red versus blue. Which one's more acidic? Okay, that took a lot longer. Okay, and the reason that might take a whole lot longer is the structures are a lot more complex. Those more complex structures take more time for you to think through and reason through. Okay, and that takes practice. The H3O plus and H2O you've seen for at least 4 years. Well, that's 2 years. At least 2 years. Okay, through your chemistry background. Okay, so you've grasped those. You're now looking at more advanced structures. More advanced structures require more time and more practice to start to understand. So when you're thinking about how hard OChem is, it's because you're trying to do something that takes a little bit of time to process. So you have to continue to practice. Okay, so how do we evaluate? What was our rule between H3O plus and H2O? Where do we start? Close. We didn't start with charge size. We had to get to a place that allowed us to use that. What was the first step we did? We removed the H. We looked at the conjugate base. Now that we have the conjugate base, we can see where our electrons are. Because we can now see our electrons, we can now start to have this conversation about charge, size, electronegativity, resonance, and induction. So where are the electrons in our red and blue? On the oxygen, let's do better than on the oxygen. We should be able to get super, super specific because I've color-coded. What are the electrons we're talking about? The purple ones. Okay? Those purple ones were the one that were in the oxygen-hydrogen bond. So we're being very, very specific. We're allowing the color coding to direct us through this. So we can start and say charge. Well, we're looking at the atom that's holding those purple electrons. What is its charge? Negative. What if you forgot to include the charge? Is that now neutral? No. What does that mean? You need to make sure you're taken care of as you navigate your new drawings.
Draw good.
You gotta make sure you draw good. Okay? You've got to make sure you're including all of that stuff from OChem 1 back into this, because if you don't, it can start to make your answers a lot more convoluted and dangerous to interpret. So we can now start charge. What's the charge between each of those? On the atom that holds those purple electrons. It's negative. It's the same for both, so we don't worry about it. So we move to the next thing. We're asking about the atom size. Well, what is the atom holding those purple electrons? It's oxygen and oxygen. It's the same, which means I can't differentiate in size. So what's the next thing I do? Electronegativity. I can't differentiate in electronegativity because it's the same atom. Then I go through and look at resonance. So now I have to pull up all that resonance stuff from OChem 1 and consider those. Do I have an option for resonance? Is it different between the two?
Is there an extra carbon? Or is that?
So is that spot right there a carbon? Yes, there is a carbon there. So, is the resonance different?
No.
No. So what do we move to next? Induction. Induction. In this case, we actually get to use induction, the thing that I keep telling you to never use. Okay? You never use it because you jump to it. Move through the list. So we now get to the induction. Is there an inductive difference? And what is that inductive difference? I want you to make the correct comparison between them. Nitrogen is more electronegative. Cool. Correct comparison. Nitrogen is more electronegative than what? Okay? And this is exactly what I wanted to hear. I heard two different answers come out of this. Nitrogen is more electronegative than carbon. And I heard somebody else say hydrogen. What's the comparison I'm trying to make? You need to make sure that you're making a consistent comparison between these two. Where is the nitrogen in our blue structure? And this becomes a hard question. We could try and do a pointing option. 3 bonds away from my negative. So there's a negative. There's 1, 2, 3. Okay, so there's my nitrogen 3 bonds away. So if I go over to the other one, 1, 2, there's nothing out there. So why are you even saying carbon or hydrogen? Isn't it nothing? What's out there? An implied hydrogen. So when I'm now making the comparison between these, it's nitrogen versus hydrogen. That's the comparison I need to make to evaluate when using induction. So you have to make sure you're making the fair comparison between these structures. Okay, so I totally get where you want to go with carbon. Okay, but make sure you're making that same distance explanation all the way through. Make sense? Okay, so now that we know what we're comparing, nitrogen is more electronegative than hydrogen. Okay, what does that mean? Pulls more of the charge that it's not connected to? I am being obnoxious, but do better. That nitrogen is pulling harder on that next carbon, which then means that next carbon is pulling harder, which means that oxygen is getting pulled into the structure harder. What does that mean is happening to that charge?
It's getting less negative.
I accept. You could make the argument that it's getting less negative because you're now not having the oxygen hold on to that charge. You're actually sharing it with those other things. Kind of like resonance, except it's not resonance. Okay? It's a process known as hyperconjugation, which is a really fancy word of just saying we're using induction, which is a fancy way of just saying it's electronegativity of a nearby element.
Making this
Okay.
a more stable base.
What does that mean about the stability? Okay? If the oxygen is sharing that charge with more elements, that makes this structure more stable than this one. What was the question? Which one's the stronger acid? So you just explained why the blue conjugate base is more stable, but you didn't answer the question. What was the question? Which one's the stronger acid? Which one's the stronger acid? The blue structure up top. This is my stronger acid. If I wanted to play with my arrows, this arrow comparatively is going to be significantly larger or more forward in direction than the other one. Okay? That does not make the blue structure a strong acid. It's just stronger than the red one. Kind of makes sense?
Because it's more stable.
Because what's more stable?
Blue structure.
Is this blue structure that I've got circled more stable than the red structure?
It's less stable.
It's actually less stable. Okay? So, and this becomes the confusion with this, and it's only going to get worse here in a second. Okay? So we got to make sure that we're on top of this. When we're evaluating the reactivity of those, what we shifted to was to look to the conjugate base. Why did we look at the conjugate base?
Because it has those lone pairs that we can.
Because we can
manipulate.
see the electrons that we can manipulate. And making the comparison now between those, because now we can see it to actually decide something about stability, the blue conjugate base is more stable. Because it is more stable, what does that mean about the starting material? The starting material must be more reactive to generate the more stable product. Does that kind of make sense? How are we feeling on that? Okay. So when looking at acid strength, we go through and we look at the stability of the conjugate base. Okay? Very commonly. This is something that you did in 152 as well. You evaluate those stabilities. You talked about equilibrium, thermodynamics, and kinetics, and all that kind of fun jazz, and you quantified all of it. You may just not have realized it tied back to the actual structures. Okay? So theoretically, ranking acids should be easier for you because you've had more practice. Okay? It's something that if you go back to OChem 1, we also talked about in OChem 1 and how we rank acid strength. We just didn't pick crazy weird structures like this. We looked at simpler structures. We looked at methanol in comparison to methane. Okay? In this unit, we're now starting to get into really heavily relying on resonance and induction to explain our differences in acidity. So far, so good?
Can you say again, just like in one sentence, what, no offense, the blue part, the blue one, no, the bottom, what is that showing?
So this bottom blue structure, and for the sake of people at home, okay, if we're looking at this bottom blue structure is showing kind of a lot, and nothing all at the same time. Okay? Because this blue structure shows with this, recording again, shows resonance. Okay? And then we see all these kind of positive arrows, straight arrows. Those are showing a hyperconjugation or an inductive effect, where the positive is being shown where the electrons are getting directed towards. So we're saying the electrons are getting pulled towards this nitrogen. Okay? That's all that blue structure shows. Does that answer the question?
Yes, thank you.
Oh shit, okay, never mind. So that's all the pieces that are going on in that blue structure. If you're going to be asked to rank acid strength, what else might you be asked to rank? You might also be asked to rank base strength. Okay? So we ready to look at that? Sure, why not? Okay, eventually my pen will catch up with me here. Maybe, maybe not. For the sake of progressing forwards, the instant I start writing on the board, it's going to show me something. And let's pick something more on the simple side. So we have ammonia versus water. Still hasn't caught up with me yet. Rank base strength. How do I do it?
Convert them into their.
So let's make sure we got lots of space underneath, just like we do with the acids. Starting off with our acids, actually, what was our very, 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 very first step?
Turn them into their
Nope.
conjugate base.
Nope. You defined what an acid was. That was our very first step. So what is our base? That would be an awful definition to use. Right? You're right, but we don't want to use that.
Can accept proton.
Okay? So if we're talking about the base, we're going to encounter a whole bunch of different definitions. Okay? With acids, we said very specifically acid was referring to the Bronsted-Lowry acid. If we use the Bronsted-Lowry definition for a base, it's going to be an H plus acceptor. Okay? And yes, people saying proton acceptor is perfectly acceptable. Okay? So let's use that definition at least initially. Okay? And let's go to what our next step was in the process, which is exactly what several people went through and said, well, with the acid, we went through and looked at the conjugate base, so what should we do when we look at the base?
The base.
Well, let's go through and look at the conjugate acid. Okay? And if you're starting to draw, I would not in this case. And we now have, I didn't color code these, I'll fix that in a second. Okay, and we now have our conjugate acids. Okay, now what I want you to do is actually think back, okay, or if you're watching the video at home, you can rewind back. Why did we draw the conjugate base? What was that? Mostly right. It was charged. It didn't have to be charged. Why did we draw the conjugate base? Stability of what? What were we looking at? The electrons. The whole point of drawing the conjugate base was to see the electrons. That's why we did it for the acid. That's it. I want to be able to see the electrons so I can talk about resonance. I can talk about where those electrons are and all of that reactivity. If I go through and look at the definition of a base that I've now defined, the proton acceptor, let's take a look at our conjugate acids. What charge are they? Positive, which means what did I do to the electrons? I've actually hidden them. Necessarily, by drawing out the conjugate acid, I hid the electrons from view. The whole point of drawing the conjugate base when talking about acid strength was so that I could see the electrons. If I use the definition of a base of Bronsted-Lowry and try to rank the base strengths, and I now look at the conjugate acids, I'm making life more difficult because I'm removing my ability to actually interpret where the electrons are. So let's take a step away from that H plus acceptor. How did it accept H plus? It was an electron donor. And in particular, it was an electron donor to a hydrogen. That hydrogen's coming from the acid. Which means if I'm now looking at base strength and trying to rank them, I don't want to look at the conjugate acid because the conjugate acid doesn't have the electrons. Where are the electrons? In the initial base structure. So on the nitrogen, it's that one lone pair. On the oxygen, it's again the one lone pair. I can only donate one lone pair at any given instant. Right? I don't need any of this other stuff to evaluate now. I start with the base structure because my focus is on the electrons. That's the only thing I'm trying to do. Right? So now I can start. Charge. Are either of those charged? The atom holding the reactive lone pair, nitrogen versus oxygen, they aren't charged. Size. Is there a size difference? Okay? And this is where we can get a couple different answers. Again, for my class, I would say absolutely no. Okay? But you can go with not really or negligible or both acceptable. They're in the same row. There isn't a significant size difference. Which then means we move to electronegativity. Is there a difference in electronegativity between oxygen and nitrogen? Yes. What is that difference? So if oxygen is more electronegative, what does that mean?
Makes it the weaker base.
It's holding the electrons better than the nitrogen. To act as a base, what must it do?
Need an electron donor.
It must donate, which means this one's my stronger base. I would argue ranking base strengths is a whole hell of a lot easier than ranking acid strengths. I don't have to draw a whole bunch of extra structures. I'm looking right away at the structure. Does it have the electrons? And that's it. Where are those reactive electrons? Now I can use charge size, electronegativity, resonance, induction. Kind of makes sense? The challenge with base strength, as we've already discussed in going through this, is our natural reflex is to fall back on the thing that we've done the most often. And when we talk about acid strength, we've done that forever. And when we look at acid strength, our step one is to draw the conjugate base. No, it's not. It's to identify the electrons. The electrons are in the bond when looking at acid strength. That's really hard to evaluate. So I have it act as an acid, draw my conjugate base. Now I can see my electrons. When I'm looking at a base, same process. Identify the electrons. The electrons are already there. I don't need to go through a whole bunch of extra steps. Kind of make sense? Okay. So your challenge is going to be to constantly go back and forth and decide. When we talk about OChem 1, almost everything that gets asked about is acid strength. When we talk about OChem 2, you get kind of a 50-50 mix. Okay? And that kind of pushes towards what the ACS does. Okay? You'll talk about both acid strength and base strength. Kind of, sort of? Okay. After that, all it is practice. There is nothing more advanced when ranking acids and bases. This is it. Okay? As painful as that may be, it just requires lots of practice. Okay? Would you ever expect to see a multiple choice question, which one's the stronger base, water or ammonia? Why not?
Because you want to stick your rod out.
Why not see a multiple choice? Which one's the stronger acid
If
or
you're going to do
stronger base?
ammonia and nitrogen, you might as well just remember that nitrogen's more basic than
Okay,
nitrogen.
that's fair. Which, for all of these, yes, you can absolutely do that. Why else does it make no sense to ask a multiple choice question, which one's the stronger base?
True or false?
It's effectively a true or false question. Okay? So the only way I can get it beyond a true or false question is I add another thing into that structure or into that system, and now I could ask which one's the stronger acid or base, or more than likely we bring in the question of rank them. Okay? Bar none, the most common response to any ranking thing that I see students go through and do is they try to rank all three at the exact same instant. That is never the appropriate response. Pick two. Which two? It literally doesn't matter. Pick two. Rank them. Okay? And I would argue, actually, if it's multiple choice, what should you do then, once you've ranked those two?
Look for that one.
Check your answers. Okay? Because maybe just ranking those two, you actually have the answer, you're done, move on. Okay? But once you've picked those two, you've ranked, you've checked, and you have to do more work, okay? Bring the next one in. Well, what next one should you bring in? If it's only three, you're bringing in the third, but which one should you compare it to? Should you compare it to the first one or the second one? Look at your answer choices. Okay? For a multiple choice, you can look at your answer choices and see, is that the one they're testing you on? Because they're swapping the order around and now you actually have to rank it in? Okay? Or are they only pushing it to one comparison? So you can leverage your ability to whittle out certain thought processes so that you don't have to work as hard. That can make life easier. Formally, what should you do? You rank them all. Like that's, to show your work, that's what I'm going to ask. I want to see all that work explaining what's going on and you explaining each and every single one of those ranking systems.
If, let's just say does the base become more stronger the more it can check off those boxes on the right side? So let's say that less electronegativity was nitrogen, but then on the red one had resonance with induction. So there was another element that was attached to that. Is there one that, because there's two of it, then one, would it trump the other one, or would it?
So, and I know
ranking?
there are situations where you do get factors kind of trumping. Those situations are usually far and in between, particularly when it comes to multiple choice. When it comes to show your work, that's being asked by me, and being asked by me, what I'm looking for is what's your explanation. So if your explanation is internally, internally consistent, I'm fine with it. I'll point out why you're wrong, but as long as you have that internal consistency, I'm okay with it. All right? I tried to come up with something real quickly on this, okay, to evaluate this. So if we're going to go through and compare these, and this is where we need to be careful, size. Well, charge, there's no charge difference, right? Size. Which one's the smallest? Hydrogen. Because hydrogen's the smallest, is it going to be more or less stable?
Less.
Less stable, which means
Better base.
better base. Electronegativity.
The oxygen. Is there anything?
The oxygen, which would suggest the hydrogen is a better base. Which one is the least basic out of this list? This one. We just went through and said that that was the most basic based off of all these explanations. That must mean resonance or induction is an exception. Do the other two have resonance or induction? Does the H2 have resonance or induction? No. What was the first step?
Identifying the electron donors or bases.
Identifying the reactive electrons. Where are there electrons in H2? There aren't. I mean, technically in the bond, but there aren't. Which means, can H2 act as a base? No. This is why it's very critical to go back to that very first statement. What are you being asked to evaluate? And in all those cases, our primary focus is finding the electrons.
So 1A should be, or 3-1 should be
Well,
identifying what you're looking at.
yes, but charge size, electronegativity, resonance, induction are not exclusive to acids. They're not exclusive to bases. They're just a blanket statement. What are the things that contribute to stability? And in what priorities? That stability can apply to a myriad of different choices. So you should always keep those things in mind as you try to run a chemical reaction. But they aren't the thing causing the chemical reaction. You are doing the chemical reaction. You have to evaluate what you're doing first, and then you use charge size, electronegativity, resonance, induction to evaluate yourself. Kind of makes sense? Okay. All I had time to look at for the record was the acid-base play, pause it, video thing, which is why I doubled back to this. Make sure everybody was on the same page. Do you all have questions yet? Really, nobody? We're like a week since the last exam. You should have done a whole bunch of stuff. You're telling me all this stuff was easy?
Wait, there's no words there. Only one word.
2 more. Exam 3 and the final. Okay, well then we'll pause this from a couple different angles. So if we're given this as a final product, what do we have to do?
As a fun.
Mm-hmm. That's in a little locked box. You're not allowed to change that. You just got to do it. So what things change from our starting material to our product? Okay, the carbonyl carbon has a different substituent on it. Okay, so if we look at it, the overall reaction would be substitution. Okay, does it fit the pattern for SN1 or SN2?
SN1, because there's 2 structures.
That's a hard, 2 structures. You're being asked to determine the mechanism. So why are there 2 structures? Because I have a reactant and a product, and I have no idea what's happened in between. Okay, so not a bad idea, but
I think it's
when we talk about SN1 and SN2, what was the hybridization of your carbons?
No, I moved the pi bond.
That's a good answer. If we look at our structure, it's not with a pi bond. Our SN1 and SN2 mechanisms are all sp3. Okay, so this is not an sp3 carbon in that reactivity. So trying to do this as an SN1 or an SN2 sounds a bit sketchy.
Because is it instead going to push the pi bond out to the oxygen?
Okay, so let's try and run the mechanism. What do we know needs to happen?
The chlorine needs to leave.
Chlorine needs to flip it, attack.
Oh, sorry.
So our negative chlorine needs to react with that positive carbon. Okay, that would exceed the octet on the carbon. And if we exceed the octet on the carbon, what do we need to do?
Get rid of something else.
We need to break a bond.
Keep that.
Okay? So what bond is the most likely bond to break? Why is the pi bond more likely to break than the sigma bond to the oxygen?
Weaker bond.
It is a weaker bond.
Final addition.
Okay? And you just said a word, Andrew. I don't know if it was.
Final addition, right? All what we've been doing.
Damn. Yep. Good job. Totally on it.
Got confused and I realized my version of this problem starts with the chlorine on the structure. And
So, as we're now discovering, this is a grouped question, so you may not be looking at this exact same question. You could be looking at all sorts of different variations of this. Okay, so be aware of that with this one. Okay, did I finish my drawing right?
No.
No? Okay.
Your charges, man.
Sorry. That was very judgmental. Okay, so now what has to happen?
the oxygen that had the pi bond is gonna push back down, it's gonna push out the leaving group.
What's my best leaving group? Okay, that's a dangerous question to ask, okay, particularly with the scenario of the question we're being given. What does the leaving group have to be? It has to be the oxygen because
That's what the final structure shows.
that's the final structure. So me asking that question was actually kind of inappropriate because I don't care which is the better leaving group. I know it has to be the oxygen because it's the only way I get that final product. Okay, and we now have our final answer and kind of color code a little bit better. And we've now got our mechanism. Everything's put together. Okay, but now let's double back to the actual chemistry. Okay, first step. What do we think? Is there anything potentially problematic about that first step?
There's some hydrogens that could have been taken instead of attacking the unique acid.
The chlorine would remove a hydrogen, or sorry, chloride would remove a hydrogen to form HCl. Okay, for the record, that was inappropriate statements for a recording. Not likely to happen because
Or basic solution, maybe?
we probably don't have a full context to allow for that. You'd be forming HCl, and what do we know about HCl? It's a strong acid, so having the chloride come in and act as a base is a very bad mechanism to try and show. Okay, not very likely, and that's going back to the chemistry that you've been working so long and hard to learn. Okay. So I took a negative, and what did I react it with? A positive. We could think, is there a positive hydrogen nearby? Maybe. But that positive hydrogen isn't going to lead to a very productive system either. So really, I only have one option here. I have that negative chloride to attack my carbonyl. All right, how about the second step? Do I like what I did there?
Chloride would still, like, based on what we know, the chloride would be a better leaving group.
Why is the chloride a better leaving group than the methoxide? We go back to the exact same rule set that we deal with everything else. We start with charge. We're comparing
Or is it because
the negative chloride to the negative oxide.
it's bigger?
Chloride is larger in size than the oxide, which would suggest the chloride can stabilize that charge better, which would suggest that my mechanism is actually pretty trash and I wouldn't want that oxide to leave. Instead, the chloride's going to leave. How does that change this mechanism? So if I now want to correct this as best as I possibly can, how could I change this to better reflect that chemistry?
Equilibrium, just, smaller.
Right? What we should do is evaluate that very first step is not a very favorable step, I would greatly prefer to have a small reaction forward and a huge reaction backwards. I actually want to eject that chloride right back off the structure. Okay? And if that's my equilibrium, heavily favoring my reactants, do I get any of this final product? No. Okay? And so that disappears from the overall system. So why did they have you draw this out? Well, number one, do you know how to draw mechanistic arrows? Okay? And some people are like, yeah, I totally get it. Your test may say otherwise. Okay? We may need a little bit of practice. Okay? That's not supposed to be that shady or salty. It's just saying we need practice with it. Okay? I'm just as bad. You've seen me draw stuff wrong all the time too. Okay? So we need more practice. So it makes sense to force you through some practice. Okay? After having done that practice, we now want to critically evaluate the mechanism that we've drawn out and decide, was that a valid mechanism to run? So now we have to double back through and use all the rules that we've been thinking about and go, well, dang, that step didn't make sense. I would rather see the reverse step. Right? So we get mechanism practice, and then we can also get out of this, do you understand where the reaction should go practice? How could I ask, do you understand where the reaction could go?
A question about the equilibrium, if the reactants are favored.
Cool. It's kind of easier to answer that question because if you're looking at your answer choices or if you're looking at the question when we first pulled it up, it asks about equilibrium. How else could I ask about this? What's the ratio between the product and the reactant? Okay.
I was just going to say thermodynamic or kinetic.
This isn't really thermodynamic or kinetic because you aren't making any product. You're staying with your starting material. How else could you ask this? Pretend the arrows aren't all on that one. What's the product of this chemical reaction? And again, pretend the arrows aren't there. That's bothering me. I'm just going to erase the whole thing.
Probably should read it.
Ooh, now I got too many well, here, I'll just turn that into a minus sign. Okay. What's the product? Okay. I would argue asking what's the product is a little bit dicey because that necessarily forces you into that product thing. We've already had a conversation that sometimes my word choice tends to direct you in the wrong path too. Okay. So it gets a little bit gray, but you could see the question still asked, what is obtained at the end of this reaction?
Same stuff you started out with.
I get the exact same starting material. No changes. What other structures might get shown? Well, in a nod to an earlier statement, maybe, my eraser's not working now. Man. Yep, nothing works now. Maybe you get a hydrogen removed and we show an enolate. Okay? Maybe we get the chlorine substitution being shown. Those would be two great distractor answers because those are already chemistries that we would be expecting and predicting out of that chemical reaction overall. And then you would see the starting material drawn. Okay? And then some other fourth answer that I'm not creative enough to come up with. Does it kind of make sense? So there are a lot of different ways that we can ask the same content, getting back towards, is that a favorable reaction to occur? Okay? The one that's probably the most painful for you is bringing up equilibrium. And why is bringing up equilibrium painful for you?
Because it's old news.
Yeah, it's old news. Okay? We don't talk about it a whole lot. That's mostly because it's assumed knowledge. So let's break some of that assumed knowledge and actually walk our way through it. What is K? Equilibrium constant, that's fair. Yep. Ask a vague question, you get appropriately vague responses. How do you calculate K?
Isn't it concentration of products over concentration of reactants?
It's the concentration of our products over the concentration of our reactants. So if we're going to look at that first step, we really don't care about the rest because the rest didn't technically happen. What is the concentration of our products? Would we expect a high concentration or a low concentration? How would we decide? This is why we drew the tiny little arrow. That tiny little arrow means how much product do I make?
A little bit.
A very, very tiny amount. Okay, what's the tiniest amount? For me personally, I would go with 0. 0 tends to mess with numbers when we're dealing with calculations, so we could do 0.001. Okay? What's the concentration of reactants? Big, because it's being favored in this chemical reaction. So what's a big number? Okay, I heard 1 million. That's fair. I would probably just go with 100 because I get tired putting in all the zeros and I wouldn't know where to stop putting in zeros, to be perfectly honest. Right? I was like, well, I don't know how to do that calculation in my head. That's fair. What are you allowed on the exam? Put it in the calculator. Let the calculator tell you what the number comes out to be. What's the number going to come out to be? Ten, -3, 10 to the, oh, fudge me. Erase. Over 10 to the second, which is 10 to the -3 times 10 to the -2. It should be 10 to the...
0, 0, 0. 4 zeros.
4 zeros. 10 to the -5.
Oh my goodness.
Right? Is 10 to the -5 a big number or a small number?
It's a pretty small number.
That's the small number. Okay, when we talk about K's, okay, can you think of a smaller number than 10 to the -5? Yeah, I was waiting for that one. 10 to the -6. How about -1? Is that a smaller number? -1?
It's a more negative number, and it's not like a smaller number.
Okay, and that's where we're going to encounter some issues. We talk about size, negative is definitely smaller than positive. You can talk about the magnitude of the number, the absolute value, but that's not what we're talking about. We're talking about the size. It's a smaller number, but it's negative. Okay, would you rather your bank account read 10 to the -5 or -1? Okay, I would rather the positive value for my bank account than the negative value. Okay, so is a negative number fair? No, why not? Why is it impossible? How do we calculate K? Concentration of the products over the concentration of the reactants. Can I have a negative concentration? No, that doesn't make sense, which means all of our numbers are going to be positive when we talk about K. So when we're looking at answer choices, if they're giving an answer that says negative or less than 0, i.e. negative, that's wrong. Okay, it can't be that. Okay, so what's small? Less than 1. Why 1? 1 is where the product equaled the reactants. So 1 is effectively our 0 point. It's equally favoring both reactants and products. Okay, in the grand scheme, we don't want reactions like that. We want them to favor one way or the other. In OChem, we primarily want them to favor products, which means our K value should be larger than 1. So there's really only 3 values that you should be looking at: larger than 1, less than 1, and equal to 1. If OChem only cares about things being greater than 1, why do we talk about things less than 1?
For the love of chemistry.
That's a lovely answer. Thank you so much. For the love of chemistry. We want to be able to look at a mechanism and evaluate, was that a valid mechanism? No, it wasn't. Okay? We could go through and explain as we went through and did, or we could reference the equilibrium constant. Okay? So our interpretation of our own mechanism is valid for OChem. Where else would we be concerned about these K values? Well, how about any complex chemical process? Say like in biology, where every single chemical reaction is controlled by its equilibrium constant, and our biological systems have to manipulate the system to force more products or less products at any given time. So where is K going to show up again with a real big vengeance? Biochem. Right? Again, depending on the class, they'll sell it potentially differently. Usually it's just what's its relationship to 1. Kind of makes sense?
So 1 is like the midpoint, that's like a perfect
1 is your
equilibrium.
midpoint, perfect equilibrium, equally favoring reactants and products.
That's not good. Just 1.
It's just 1, yeah. See, I told you there were no numbers. There are numbers. They just aren't that bad. We didn't even get up to 1 million. I passed on that. Maybe we got 10 to the negative 5, but make sense? We good with that question? Should we look at another? So we'll go through and do this one. What do you see?
CO negative OH there. That's pretty reactive.
Okay, I like that. I see a negative OH. Yep. What was this unit about? It's not about carbonyls. That was the last unit. What's this unit about? You came in a little bit late. So everybody that was here on time, you know the goddamn answer. What's this unit about?
Acids, bases.
Something about acids and bases, yes. There it is. It's acid derivatives. Right? That's what this chapter is about, is what are all the acid derivatives. Okay, so an acid was that, right? And if we're talking about the derivatives, what we're doing is changing this. Okay? And when we're talking about the derivatives, we're changing that to not carbon and hydrogen. Why not? So there's a couple different answers for why we're talking about acid derivatives not being carbon and hydrogen there. It's not necessarily has to do with acidity. Carbon and hydrogen aren't affecting the overall chemistry of the electrophile. That's the reason we talked about at the beginning of this lecture. Okay, so we want this purple box to be something that changes the chemistry, okay, and ultimately the chemistry of that electrophilic carbon. When we're talking about our acid derivatives, that's our primary goal here. Anything that messes with that blue thing. Carbon and hydrogen aren't going to do that because they're relatively neutral species. Why else are we not going to talk about carbon and hydrogen in that spot? It's not boring.
Like maybe.
But if that was your approach, that might explain exam 2. What was exam 2 about? Where that purple box was carbon and hydrogen. Go back and look at all the questions that you went through and did. It was when you had aldehydes and ketones. Okay? That was unit 2. We've already talked about it. That's why we're not dealing with that. Okay? We already talked about it. So what's another thing that you might notice? I love the hydroxide, by the way. What's the other thing you might notice when you go through and look at where we're starting?
You got non-polar tri-bond with bromine.
Okay, fine. Still the truth. Okay, we still got bromine. What else do we notice?
Did we not lose a carbon?
Don't even worry about that because they're trying to draw things without drawing things. They're trying to give you the opportunity to screw up. What are you reacting the bromine and the hydroxide with? Said another way, are you reacting the bromine and the hydroxide with an acid derivative?
Could act as an acid.
What did we define our acid derivative as? The polar pi bond next to something in purple that would affect the chemistry of that, where it is not carbon and hydrogen. And when we look at that starting material, it is carbon and hydrogen. So why are you being asked this question? If our whole chapter is about acid derivatives, why are we working through a reaction that does not show an acid derivative?
Review. Is there something in the mechanism that we're going to see in acid derivatives?
Oh, so maybe as we navigate our way through this, an acid derivative should pop up. Yes. Okay? And so when we go through and look at this, you should be seeing that appear. I'm surprised you didn't call it out like right away, because you've called it out like every other time it's appeared. Yes.
Did I?
Yes. Called it out at least twice in past lectures. What happens in this reaction? The base targets are alpha hydrogen. Okay, what does that do to the alpha hydrogen?
Gets pulled off the structure.
Cool. Yep. What are they trying to do? We may have to look at the solution on this because there are hints here that look a little weird, a little sus. Now what happens?
You know, you can do an attack on the bromine. Yeah.
Oh, I know what they did. It was a dipstick maneuver on their part. Is that why people say I'm judgmental? Damn. So we've got our bromine now connected to it.
But that's a more acidic.
Now the hydrogen was more acidic, right? So what happens? Okay, the OH comes in again, removes, whoa, there's a fun arrow. Removes that hydrogen and it does it again. What the hell is that?
That's a good lead right there.
That's a good lead, but I don't have that.
Not yet.
Yeah, not yet. There's the issue that I have with this. Okay, so what I think they're actually trying to set you up with and do on this is they want you to go, hey, if you have Br2 and hydroxide, what happens? You have the alpha hydrogen. You have the alpha hydrogen that does the substitution with the bromine. And how many times does that happen? That happens 3 times. So this very first step is not a mechanism. This very first step is get to that product. That product that we saw in the last unit. Now that I have that product, what happens? What do you mean? It's right there. Oh, why aren't they showing it? They aren't showing it because they're trying to not give away what's happening within it. That's all that's happening. So what I mean by that is they're just giving you a starting structure to work from. So from that starting structure, what do you need to add to it? Well, I need to add my oxygen. Okay, and that oxygen needs to have a carbon with 3 bromines on it. And it's also going to have an OH connected to it. How do I know that? Because from the previous stage, this comes in and attacks, it breaks the pi bond in my nucleophile addition. Okay, that nucleophile addition sets me up with that negative charge. The negative charge comes down and now kicks that out. There's my friggin' leaving group. Okay.
We got the thing we're doing.
We got the thing we're doing?
Yeah, it's
What does that mean?
acid.
Oh, yeah, there you go, cool. And we now have our acid. Okay, not technically an acid derivative, but we now have our acid. Okay, our acid that happens to be really close to a negative oxygen. So what happens? Okay, and you would form, what the, oh man, sometimes I really hate how they do that. You would form your negative structure. You would also get CHBr3, which is known as bromoform. Bromoform would then be neutral and kind of go off into solution. Depending on solubility, it might turn into a precipitate, but I actually don't think it does. I think that only happens with the iodoform. Right? How do we finalize this reaction? Step 2, we now add our H3O+. The H3O+ reacts with the hydrogen. And again, they've only given you the skeleton piece on that. Make sure you get your lone pairs. That piece right there is now that piece right there. Everybody see that? So was really judgmental, but it's not judgmental against you, it's judgmental against smart work. Okay. I'm gonna hope that when you click in each of those boxes, they tell you, give you a little bit more guidance on what they wanted. Because it looks like trying to do a full mechanism, but they didn't ask for a full mechanism for that first step. They really just wanted you to draw the product of that first reaction. Then they're going to have you go through and do the mechanism for the rest, because the rest fit each of those boxes.
It says in the first box, it says after reacting with 3 alpha hydrogens. And then further.
See, I was judgmental for no reason.
I think it was the.
Which is, I mean, generally true in all cases, right? We're judgmental and we're usually wrong about being judgmental.